Hello, I'm going to talk about rotational kinetic energy. So sometimes I use RKE, sometimes maybe using KE and then with the R there. Okay, so when you have a 3D object and it rotate around here, so this is a 3D object. So you look at a point, and that's a point mass, that's called that a delta M1, okay? And this is your R, okay? So then at this location, so if I have an omega, they're going like that. So remember the omega is common, right? Omega is common, so it's the same for all the point particles, right? So let's say another point here, which is delta M2, right? So common for all point mass. Delta M1, delta M2, blah, 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 right? Okay, and this one here will be R2, and that's R1, okay? And let me change the color here. So if this is turning, then this one here probably will be doing something like that, right? So this will be a V1, and this V1 will be equal to R1 times omega. And this side here, this V2 will be probably going this way, and the V2 will be equal to R2 times omega. So we do all of this and add them together, and we're going to call that, that's the rotational kinetic energy. Rotational kinetic energy is equal to, right, so that's the title, equal to 1/2, right, summation of 1/2 delta M I VI square, right? So I from 1 to, depends on how many pieces you have, okay? So that's what you have. And we're going to substitute the VI, right? So 1/2 delta MI, and this VI will be equal to RI times omega, right? And this is square, right? So VI square and RI omega, so square. So omega is common, 1/2 common, it's going to come out 1/2, and then omega square, and that becomes delta MI RI square, and I from 1 to n. And this is our definition of moment of inertia, right? I, capital I, moment of inertia, right? Or rotational inertia, okay? So then this is equal to 1/2 I omega, right? So then that's your formula right there for rotational kinetic energy, okay? All right, so now we're going to extend this and just say that now it's not just a rotation. Let's say we have something that's turning, let's say down the slope, right? So then we know the center of mass is here, and center of mass would have a velocity that's going like VCM, that's center of mass. At the same time, it will be doing the rotation like that, okay? So then when this object is doing that, your kinetic energy will be equal to kinetic energy of rotation plus kinetic energy of translation. Okay? So then this rotation here will be 1/2 I. Let's say this is a disk. Okay? So then with I, right? This I for the disk, right, will be 1/2 mr squared, right? And this will be your R, and this mass will be m, and this is solid disk, for example, right? So that'll be 1/2 I omega, right? And then plus the translation. This translation is coming from Cm, right? So your whole, everything is going down, right? And you can assume this, everything is concentrated inside the Cm, right? So when it's coming down, everything Every single point is coming down, following the center of mass. But at the same time, he's doing the turning. So this is the pure translation plus the pure rotation, right? If this is rolling without slipping, right? Rolling without slipping, like we talked about before, okay? So then this one here, the translation, this one will be 1/2 the m center of mass, right? So the entire m, this m here, times v of the center of mass, right? And that's your formula, okay? All right, so I'm gonna stop there for the day, okay? And until next time.